So, the Complex Cube Part 1, Imaginary Pieces. This is going to be another semi-rambling thing, except this time I sort of have a sort of script, and there's going to be animations or slides which I hope should help. I'm not entirely sure yet, because I'm recording this before I make any slides, so there probably will be videos, but I'm not sure yet. But anyway, this video is going to be an exercise in taking a limited dataset and extrapolating in a sort of ordered way so you can start to make sense of things. So, if we start with just a normal 3x3, we're going to construct the complex cube from the ideas you can get in a normal 3x3. So, if we break a regular 3x3 and arrange the pieces, we find that there are three different types: corners, edges, and centers. And I'm sure all of you already knew that. So, and you also knew that we can refer to each piece by the position it should be in when it's solved. So, UBR, whatever. And while it's all very well to have these classifications, corners, edges, centers, it might be more satisfying to work out the properties of each piece and what we can do to assign them. So the easiest way to do this is to count the number of stickers on each piece. Corners have 3, edges have 2, and centers have 1. And one other thing we should note is that we can't interchange pieces with each other. Corners stay in corners, edges stay with edges, centers stay with centers, no matter what move we do, because this is a normal 3x3 and not a mix-up cube or anything. Now, we can say that this means each piece is in a different orbit, and just from now, there's going to be a series of footnote videos which will go into slightly more depth on the things that I just mentioned in passing. So, the first one will be on orbits, which is basic group theory. By now, some of you might have noticed I left a fair amount of space at the bottom of this table and be asking why. Well, if we organise the pieces into these categories, we notice something interesting. While we have all the different combinations of one sticker for the centres, we're quite a few short for the centres, for the corners and edges. So we could have UD or UFB or ULR or whatever. Now, on the face of it, it's quite obvious these pieces can't exist because you can't have a piece with both a U and a D sticker. But for now, let's pretend we're mathematicians and not care about whether or not these pieces really exist and investigate what might happen if they did, because it's a fairly interesting question. So we'll ignore the centers for the most part because you can get all the combinations of one sticker and they're pretty boring and don't really move around when it comes to things like non-slice turns. So the first question we might want to ask is how many of these imaginary quote-unquote pieces exist. This is a reasonably simple exercise in combinatorics where we use the choose function, which is a C on a lot of calculators and is denoted like this. And it works out how many combinations we can make if we choose a certain number of pieces from a set of a certain size. So, it's given by this formula, where these things are the factorial function, and if you want to see how we get this formula, there'll be another footnote on that. But for our purposes, we put how many stickers we can choose from, which is 6, here, and how many we are choosing here. So if we start with edges, we have 6 possible stickers to choose from, and we want to choose 2 from that 6. So putting it into the formula, we find we can have 15 combinations of 2 stickers, and for the corners, we find that we have 6 possible stickers, and we want 3 of them, which gives us 20 combinations. Now, we know how many pieces we want to update this table. So, if we put in the new imaginary pieces, and we know that we won't miss any because we just worked out how many there are, I'll put the new imaginary pieces in orange. So, imaginary corners, imaginary edges. The next logical question we could ask is how these pieces would move with each turn of the cube. Now, clearly on a normal 3x3, they wouldn't really do anything, but we're extrapolating again, we're pretending to be mathematicians. So, if we look at the real pieces and how they react, we can represent each piece like this in a column vector, with each position it should be in order. Now, if we break it down and look at just the stickers under a U move, we see that the only pieces that are affected are those which have a U sticker. So looking at just the UFR corner for this case, we see that the U stickers don't change, but the L stickers become B stickers and the B stickers become R. And if we do it again, we find that the R become F and the F become L. And if we do it again, so on and so on. If we look at the edges, we find that exactly the same thing happens. U is unaffected, B becomes R becomes F, F becomes L, and so on. Now, if we continue these patterns for the other turn, noting that the sticker of the move and the opposite aren't affected, we can leave them out and get this for the general case. So, U move, D move, other four, and the other four. So, we find this pattern in general, and there'll be a link to this chart in the description. So if we apply this pattern to the imaginary pieces, we find that the pieces must move in this pattern. So under a U move, the UDF piece moves to UDL. Under an F move, the FLR piece becomes FUD. And under an R move, the LFB piece is unaffected. A graph of how the pieces move will probably be in the description. Depends if I have the time to make that huge, massive chart with all of the pieces on it. So that is a brief summary of what a normal complex cube is. Well, a quote-unquote normal complex cube with imaginary edges and imaginary corners and how they might move around. So, we've defined one way to make a complex cube, and be sure to check the footnotes if you want to have a brief overview of any of the things that I used in this video, just skimmed across them. I'll be releasing these videos fairly sporadically because making a lot of slides is hard enough in general, and I'll try to make footnotes within the next, I don't really want to commit, maybe 1 to 2 weeks after this video. And just as a final note, there are alternative ways to define a normal complex cube. For example, a U move doesn't actually affect any piece with a D sticker on it, for example. So next time, in part 2 of this, which will be released after I make all the footnotes, we'll discuss the hypercomplex cube, which has super imaginary pieces, which has pieces with, say, 4 stickers or 5 stickers, or things like that, which also can't really exist on a normal 3x3. But that's all for now. Be sure to check the footnotes, and if you have any questions, ask them in the comments, message me on SS, message me on Reddit, any of that sort of thing, and I will see you guys in 2 days with probably another 42 ALG case.